Hey guys, this is the last part from vector spaces. Um, Unfortunately, I have to redo the video again since the last video was without any sound. Anyway, sometimes things like this happen. In this video, we'll cover very extensive material such as basis and dimension of a vector space. Then we're also going to cover the rank of a matrix, which is a very important notion. And we'll see the relevance of the rank of a matrix concerning systems of linear equations. Also, another thing that we will cover in this video will be coordinate and change of basis in a vector space. So let's get started. So we will start with basis and dimensions of a vector space. And fortunately or unfortunately, well, I usually don't like to read from notes usually, but anyway, since I have already all of them written down, I will do it. So let's start with basis and dimension. As you can see the definition here, probably it will go faster, I assume. So the definition of a basis, we have this set of vectors S, V1, V2, Vk, and this set of vectors is given in a vector space V. And we say that this is a basis for V, this set is a basis for V if the following two conditions are met. And the two conditions, as you can see in this written with red, the first are the following. The first one is that this set spans the entire vector space V. And the second condition is that this set is linearly independent. In other words, we have the vectors inside from this set S are linear independent. And now let's see an example. A very easy example to see is this, as you can see here, the set of these vectors in R3. And clearly you can observe the fact that these three vectors are the standard vectors in R3. So the first one is 1, 0, 0, the second one is 0, 1, 0, and the third one is 0, 0, 1. So these are the three vectors in R3. The question is, does this form a basis for R3? Well, we need to see it. Well, as you might expect, the answer should be yes. So the two conditions we need to verify based on, if we look at the definition of a basis, are these two conditions. So the first one is S will span V, and the second one, S is linearly independent. Clearly, that's obvious that any vector in R3 can be expressed as a linear combination of vectors in S. As you can see, if we consider V to be, let's say, a vector of coordinates x, y, and z, and this clearly can be written as x times xe1 plus ye2 plus ze3. So we have a linear combination of these vectors. Clearly, this will span the entire vector space. Also, the second condition we need to verify is that that S is linearly independent. Well, by the definition of linear independence that we have talked about last lecture, the lecture before this, is that the set S is linearly independent if the vector equation, this one here, C1E1 plus C2E2 plus C3E3 equals 0, has only the trivial solution. So there is only the trivial linear combination for this. This is the only combination possible. Okay. At the end of the day, if we write them out, and if we do the standard operations with vectors, if you look at this vector equation right there, right here, C1E1 plus C2E2 plus C3E3 equals 0. And if we do, like I said, everything, we do all these computations, we multiply vectors and everything, clearly you will see that you'll have after some computations, you'll have that C1, C2, C3, this vector in R3 is the null vector. So therefore, the components must be all equal to 0, and that's it. So it's very easy to see. All right, so this is the first example. Clearly, this is a basis for R3. So the answer is yes. And now let's see a second example, which is not as trivial as you might think. Now we will consider a set of vectors in R2, of two vectors. And the question is, well, it's the same question. Is S a basis for R2? Well, to see this, we need to go back to the definition. So let me go, the definition is right here, you see, for the basis. So we need to check these two conditions. So we're gonna do the same thing here. So the first one is that, the first condition that we need to verify is that S spans R2. Well, we consider a vector x equals a vector in R2, and to show that x can be written as a linear combination of vectors v1 and v2, we have to consider this equation, the so-called vector equation, c1 v1 plus c2 v2 equals x, which is x1, x2. And once we do the algebra here, we do the operations, well, clearly we'll get this system right here. C1 plus C2 equals X1 and C1 minus C2 equals X2. And now we're wondering about this system. How can we solve this system? Well, we have the following important fact that you need to know. The coefficient matrix of this associated to this system has non-zero determinant. So if we see this, this means that the system S has unique solution. In other words, this will imply that S will span R2. And now let's look at the coefficient matrix of this system. If you look here, the coefficient matrix of the system is given by, and the determinant, we have to compute the determinant of this. And if you look, this is nothing else than just the determinant of the matrix with the entries. On the first row will have 1, 1, and on the second one will be 1 and negative 1. Well, it's an easy computation to see that the determinant of this will be negative 2. Well, it's not hard to see, which is not 0. Therefore, by this observation above, clearly the system S has unique solution, so S will span R2. The second condition we need to verify so that we can conclude that S is a basis in R2 is to see whether S is linearly independent. Again, let's consider, in this case, we'll consider x1, x2 is the null vector. And again, I will go back to my system S, and my system S will be, this time will be a homogeneous system. So as you can see, I will replace, if we go back here, so you see I have the system S, C1 plus C2 equals X1, and the second equation is C1 minus C2 equals X2. And this time I'll consider X1 and X2 to be 0, 0. So the system, like I said, will become a system of a 2 by 2 system, a homogeneous system. And this is trivial to see that this has only the trivial solution, right? I said this, I'll leave it as an exercise, but it's instant. You can instantly see this. So again, we can conclude that S is indeed a basis for R2 since S spans R2 and S is linearly independent. Okay, this is the second example. Now, the third example that I have in mind, and I want you to look at it, is this set of vectors in R3. As you can see, these vectors are not, they're just randomly, I picked some random vectors in R3. So S is, the first one is 1, 2, 3, the first vector. The second one is 0, 1, 2, and the third one is negative 2, 0, 1. The same thing, the same question I want to ask. Is this a basis in R3? Again, we need to check this. If we check these two conditions from the definition, if S spans R3 and S is linearly independent, then clearly we can conclude that S is a basis for R3, right? Okay, so let's check these two conditions. In fact, I will just leave it as an exercise since it's not easy, it's not hard to see. And now let's see another example, example number 4. Let's look at it. Example number 4, this time I will consider a set and the elements of this set are 2 by 2 matrices, right? So this is, these are the elements, the vectors of this set are 2 by 2 matrices. And as you can see them, all the matrices are, they have one in one corner, right, top right, top left, bottom right, bottom left, all of them. So we have all these combinations. And I want to see if this is a basis for M22, which M22 will denote by as the set of all 2 by 2 matrices with real entries. Okay, well, you can kind of see it immediately that this guy expands the entire vector space, which is M22 in this case, since any matrix, any 2 by 2 matrix, let's say A, B, C, D, can be expressed as a linear combination of these 4 matrices. But let's see it. We can clearly see it here. If we write it like this. And well, this is just an easy computation, right? So, and moreover, it's quite clear that if we have this this linear combination here, in fact, I didn't write this, but the second one, so S is linearly independent, since any linear combination, so if we have something like, let's say A times 1, 0, 0, 0 plus B times 0, 1, 0, 0 plus C times 0, 0, 1, 0 plus D times 0, 0, 0, 1. This will be 0, 0. Well, automatically this will give us that A equals B equals C equals D equals 0, right? So this is just, it's easy to see, it's trivial to see that. Anyway, now let's talk about the following theorem. And the following theorem will concern the uniqueness of a basis representation. So if I have a set of, if I have a basis, let's say S of vectors with V1, V2, Vk, for my vector space V, then every vector in V can be written in only one way as a linear combination of vectors in S. So I have uniqueness here. I think the statement is pretty clear. It says, and now let's see some an example. Let's look at this example. So I considered a vector in any vector in R3, which is denoted by U1, U2, U3. And I want to show that the equation U equals C1, V1, so this vector equation that we have talked about, C1, V1 plus C2, V2 plus C3, V3, has a unique solution for the basis S, which will consist of these vectors, which v1, v2, v3, that you see here. So the first one is 1, 2, 3, the second one 0, 1, 2, and the third one negative 2, 0, 1. All right, so let's see this. We just have to do the vector equation. So once we do the computations, we want to write up the vector equation, which is u1, u2, u3 will be c1 times the first vector from times v1 plus c2 times v2 plus c3 times v3. But once we know who v1, v2, v3, we know who these guys are, so we just plug them in. And at some point, you'll get again a system S, right, which will 3 by 3 system, and this time you have u1, u2, u3, right, and then we can write the system in the matrix form. And guess what? The same story applies as previously. This will have a unique solution once we know that the determinant of this is non-zero, therefore the matrix is invertible. Anyway, and by finding the inverse of A, and I'll leave it to you as an exercise, we'll deduce that C1 equals negative 1 plus 4 U2 minus the 2 U3. C2 will be 2 U1 minus 7 U2 plus 4 U3. And C3 will be negative U1 plus 2 U2 minus U3. Well, the computations have been done already. And for example, if we take in particular, if you take U to be 1, 0, 0, this can be represented uniquely as negative V1 plus 2 V2 minus V3. Okay, and that's it. And now let's state we have the following theorem for basis and linear dependence. The theorem, as you can see, states the following. If I have a set, right, S of V1, V2, consisting of these vectors, V1, V2, Vn, basically I have a basis for a vector space V, then every set containing more than n vectors in V are linearly dependent. So I cannot go beyond the number of vectors that are in S that form a basis. And now let's see an example. So R3 has a basis of 3 vectors, right? So this set, as you can see here, I have more than 3 vectors. I have, if you look at the set S, I have 1, 2, 3, 4 vectors. So therefore, they must be linearly dependent. That's quite clear. And now we have the following theorem before we go further and discuss about the dimension of a vector space. We have the following theorem. If a vector space V has a basis with n vectors, then every basis for V has n vectors. Well, this is quite obvious. Okay, now let's talk about the dimension of a vector space. So the definition is the following. So if I have a vector space V, has a basis which consists of n vectors, right? This is a very important thing to say. A basis consisting of n vectors, then the number n, guess what, is nothing else than just the dimension of that vector space. And we'll denote this dimension by, well, as you can see it here, the notation is this one here. The dimension of V is n. When V consists of the 0 vector alone, the dimension of V is defined as 0. That's the definition. And now let's see some examples. For example, the dimension of Rn. If we take this vector space Rn, the dimension of Rn clearly is n. for example, if we take another vector space, such as the vector space of n by n matrices, so the square matrices of size n, or order n, the dimension will be n times n, which is n squared. Or if we take the vector space consisting of all m by n matrices, the dimension of this space will be m times n. Anyway, this is very simple to see. And now that we have the following question, how do we find the dimension of a subspace of a vector space? So, given a vector space, and I have a subspace of a vector space, well, maybe I know the dimension of that vector space. Now the question is, how do I find the dimension of that subspace of the given vector space? Now let's see some examples. The first example I have in mind is the following. I need to find the dimension of the subspace W of R4 spanned by this set, spanned by S, which consists of these vectors in R4. So I have three vectors in R4. As you can see, the first one is given by -1, 2, 5, 0. The second one is 3, 0, 1, and -2, and the third one is 5, 4, 9, and 2. Okay, let's see. The first question I need to address is S a basis for W? Well, clearly the answer is no. S is linearly dependent, right? That's obvious to see, because I can express one of the vectors as a linear combination of the other two. In this case, V3, if we look closely at my set S, you will see that V3 is nothing else than just a linear combination of the first two vectors of V1 and V2. More precisely, V3, you can express it as 2V1 minus V2. So the answer to this question is no. S is linearly dependent. Also, if we look, W is spanned by this set of vectors, right? By this S1, which will consist of the first two vectors. And I'll leave it to you as an exercise to see that these first two vectors are linear independent. Well, in other words, S1 is linearly independent. So therefore, the dimension of W will be 2, and that's the dimension of this. Now let's see another example, and we have seen previously. And now I'm going to consider the subset of all 2 by 2 symmetric matrices. And as you can see here, we've said previously that any matrix can be expressed as a linear combination of those 4 matrices, right? With the first one with the 1 on top, left top, then the second one was top right, and so on, right? We have 4 matrices. Well, in the case of 2 by 2 symmetric matrices, any 2 by 2 symmetric matrix will look like this: A, B, B, C. Well, symmetric. So let me remind you that any symmetric a matrix is symmetric if it equals its transpose. So as you can see here, this can be written as A times this matrix, the first one with 1, 0, 0, 0, 0, plus B times 0, 1, 1, 0, and the third one is 0, 0, 0, 1. So this set, consisting of these 3 matrices, spans the subspace of all symmetric matrices. Let's call this W. Clearly, as you can see, I have 3 linear independent vectors here. The dimension will be 3. This will be the basis. All right. And now we have the following theorem. So I'm going to consider V to be a vector space of dimension n. The first says the following: if, and I have said it previously, but anyway, let's state it clearly now. It says the following: if I have a set S of consisting of these vectors v1, v2, and vn, if this set is linearly independent in V, then S is a basis for V. So it's enough for me to see that it's linearly independent. And also, if provided that the vector space is of dimension n. And the second one, if S spans V, here I think it's a mistake anyway, that's Vn. If S spans the entire vector space, then S is the basis for V. Well, that's the theorem, which is very useful. And now let's veer towards something else. Let's talk about the rank of the matrix and systems of linear equations. So this will be the second part of our talk. It will be quite consistent. The first thing I want to talk about is the row space, column space, and the rank of a matrix. And I want you to look at this. So if I write the matrix A as A11, A12, A1n, so I'm writing the usual entries for the m by n matrix. You can easily identify the rows, right, and the columns of the matrix. The rows are A11, A12, A1n, and so on. And similarly, the m by 1 matrices corresponding to the columns of A are the column vectors, which I will write them like this. I want you to see the rows and also the columns of A, right? The columns are, for example, if I look at the first row, will be A11, A12, A1n. The first column would be A11, A21, AM1. So as you can see them here. Okay. And now let's give the following definition. Let's consider a matrix A, an m by n matrix, or a non-square matrix. And we'll define the row space of A. The row space of A, as you can see, is the subspace of Rn spanned by the row vectors of A. And the same thing will happen for the column space. Again, this is the subspace of Rm this time, spanned by the column vectors of A, right? And now we'll have the following theorem, which will concern the basis for a row space of a matrix, and which says the following: if I have a matrix, if a matrix A is row equivalent to a matrix B in row echelon form, you see, as after we do those row operations, elementary row operations to them, after performing these operations to the matrix A, we'll obtain a matrix B in row echelon form. So if I have a matrix A that is row equivalent to a matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. This is very important, and we will use this theorem for our purposes. And let me give you an example. And I want you to look at the statement, at the statement of the theorem, also to look at the example. So the example says, so I want to just stress this again because this is very important. So if I have a matrix A, which is row equivalent to a matrix B in row echelon form, then the non-zero row vectors of B will form a basis for the row space of A. Keep that in mind. And now let's see the example. We need to find a basis for the row space of this matrix. As you can see, it's a 5 by 4 matrix. Oh my, it looks quite ugly, but anyway. ugly, but not that ugly. I don't know how to say it, but anyway, it's so this is 3 here. I don't see any pattern with this matrix. Anyway, probably I'll just pick a. It's a 5 by 4 matrix, and we need to find a basis for the row space of A. Whoa. In other words, we need to do elementary row operations with this, and I'll leave it to you as an exercise since I don't want to write echelon forms around here. So I'll leave it to you as an exercise. So by elementary row operations, A is row equivalent with the matrix B in row echelon form. So matrix A, after we perform those elementary operations, will be written, we will obtain the matrix B in row echelon form, and as you can see, it looks like this. 1 3 1 3 0 1 1 0 0 0 1, and as you can see, the last two rows are 0. So definitely I'll pick for W1, W2, W3 to form a basis. So this will be my basis for the row space of A. Let's see another example. Find a basis for the subspace of R3 spanned by S, which is V1, V2, V3, and will consist of these three vectors, as you can see here: -1, 2, 5, 3, 0, 3, and 5, 1, 8. All right. Well, we will use these vectors to form the rows of matrix A. So let's do this, and we'll have this matrix. Well, it's quite clear to see that we can form this matrix. Okay. And if you look at this matrix, -1, 2, 5, right? This is the first vector. And now we want to perform elementary row operations to this matrix. And again, if we do this, guess what? We will obtain the following matrix B. So the row echelon form of A is this matrix B, which looks like this: -1, 2, 5, 0, 1, 3, 0, 0, 1, 0, 0, 0. Last row will be 0, will consist only of zeros, so I will keep the first two rows, W1 and W2. So this set, which will consist of the first two rows, will form a basis for the row space of A. That is, they form a basis for the subspace spanned by S, which will consist of these three vectors, and that's it. And now we're in the position of giving the definition of the rank of a matrix. And okay, I'll give you this definition, and at some point in this lecture, I will show you another method of how to compute the rank of a matrix. Well, it's equivalent to this definition, but I will show you another method of computing the rank of a matrix using the determinant of the matrix. So I kind of want to relate it, this with notions that you have learned in previous chapter number 3, I think, which was about determinants. So the rank of a matrix, the definition is the following. It's, as you can see it's pretty clear. The dimension of a row or column space of a matrix A is nothing other than just the rank of A. So the dimension of so you look at the row space or column space, and you look at the dimension, and that's the rank of A. And usually we denote this by rank of A. And now let's take an example, and I want you to look at it before we even talk about this. As you can see here, this matrix it's a 3 by 4 matrix, right? I have 3 rows and 4 columns. This is not a square matrix, right? So we want to compute the rank of this. Well, we want to use, let's look at the definition. That's what we know so far, the definition. In other words, we need to find the dimension of a row space or column space of a matrix A. We need to find the row space or the column space of the matrix A. Again, we'll take this matrix and I will leave it to you as an exercise to show that by, again, elementary row operations that you will perform to the matrix A, you'll get the following row echelon form of A, which is matrix P, and it looks a little bit like this. 1, -2, 0, 1, 0, 1, 1, -1, 0, 0, 1, 3. Wow. Okay, what can you say here? If you look at this, how many non-zero rows has? Well, has 3 non-zero rows, right? So the rank is 3. Pretty easy, huh? And now, like I said, let's answer this question. Is there another way of computing the rank of a matrix? And here, like I said, I'm trying to involve notions that we learned in the previous chapter. Well, I already said it. I'm trying to involve the notion of the determinant of a matrix. Well, the answer is yes. And I'll give an example. In fact, not just one example, a bunch of examples. Again, let me look at this example. Let's look at this matrix. Well, I already circled this. Maybe I shouldn't have done that, but anyway. I'll explain immediately why I did this. So this is a square 5 by 5 matrix. And I want to find the rank of this matrix. As you can see, this matrix has something in particular. If you look at the last column, the last column it consists only of zeros. So I want to find the rank of A. Now I'm just going to give you the rank of the matrix is the order of the largest non-zero square submatrix. So we look at the largest non-square submatrix, and we want to compute the determinant of this. So the first question I need to answer is there, well, the maximum so the rank will be less or equal than 5, that's obvious. And the first question I want to answer is there any non-zero square submatrix of order 1? Well, any non-zero element is a square submatrix. So the rank will be at least 1 and at most 5. Okay, great. I knew that from the beginning. And now the second question, I want to go a bit further. I want to look, is there any non-zero submatrix of order 2? Well, let's look, and I look at this guy here. This is like boxed in red, and I want to compute this. The determinant of this submatrix 2, 1, 3, 2, which is 1, is non-zero. Okay, so so I go up a bit. The rank will be at least 2. All right, let's go even further. Question 3. Is there any non-zero square submatrix of order 3? Well, let's look. Well, let's look at this matrix. 2, 1, 2, 3, 2, 1, and -1, 1, 7. And I'll leave it to you as an exercise to show that the determinant of this is 0, and we have done it before. And also, if I look at, so 2, 1, 2, if you look at this one here, 2, 1, 2, so if I take, right, and So basically I look at these minors. The second minor, and again, I will leave it to you as an exercise to show that these are, all three of them are zeros. So unfortunately, I didn't find any minor, non-zero minor, so I have to stop here. The rank, I cannot go further, so the rank will stop at 2. That's it. So the rank of the matrix is 2. All right, let's take another example. Let's find the rank of a matrix. This time I'll pick a 3x4, a non-square matrix. As you can see it, I have 3 rows and 4 columns. And the matrix looks like this, as you can see it. And again, I want to find rank of A. Like I said, the maximal minors have order 3. And let us compute the one by deleting the last column, right? So we have the following, right? If we compute the last one, which one is given by 1, 0, 2, 0, 2, 4, and 0, 2, 2. And we're lucky, the determinant will be non-zero, so I can stop here. The rank will be 3. Anyway, always when I have a non-square matrix, the rank, so let's have, I have an m by n matrix, the rank will always be less or equal than the minimum between m and n. So in this case, it is right from the beginning, right from the start, the rank will be, rank of A was less or equal than the minimum between 3 and 4, which is 3. So the rank was less or equal than 3. In fact, it's actually 3 because we find the minor of order 3, which is a non-zero minor, and we're done. We can stop here. All right, let's see another example. Let's look at this matrix. Again, I'm picking another 3x4 matrix, which has, as you can see it, it's here. Oh, I don't know how I, okay. I usually put them in, brackets like this, not just parentheses. Probably I took it from some Romanian book because we usually in Romania, we put them in matrices, we put them in parentheses, not brackets. So we need to find the rank of this matrix. Again, the rank, by the definition, we know that the rank will be less or equal than the minimum between 3 and 4. So the rank will be less or equal than 3. We know that. And if I look at the minors of order 1, definitely will be greater or equal than 1. So I have 3 options, 1, 2, or 3. Let's see. And now let's look at the minors of order 3 because I want to get as high as possible. And let's look at them. So we have 4 minors of order 3. You can see them here. The first one is, let's look at the first one. 1, 2, 1. You see, I take the first 3 columns. And surprisingly, the determinant of this 3 by 3 minor is 0. Wow. And I will leave it to you as an exercise to show that the other 3 minors are also 0. Well, since all minors of order 3 are 0, then the rank must be strictly less than 3. So I have to go down a bit. So I have only 2 options right now, 1 or 2. And now let's check the minors of order 2. The first one is what? Let's look. The first one was, if we go back, is 1, 2, 9, 5. The determinant of this minor will be negative 13, which is non-zero, and I stop here and that's it. It's not necessary for me to compute any other minor, so I can conclude directly that the rank of A is 2. And in fact, you can also see that the first 2 columns of A are linearly independent. If you want to use the classical definition of, well, the definition of the rank of a matrix. Let's see another example. this time another 3 by 4. Looks like I have something with a 3 by 4 matrix. Again, the same story applies here. Again, this is a non-square matrix, a 3 by 4 matrix. So again, the rank of A will be less or equal than the minimum between 3 and 4, which is 3. And if I look at the one minor of order 1, I just pick any. All of them are non-zero, so I have no problems. The rank clearly would be, I have 3 options, 1, 2, or 3. Now let's see. Let's compute the minor of order 2. 1, 2, 4, 5. So clearly this is non-zero. Okay, so clearly I know at this point that the rank is at least 2. So let's go further for minors of order 3. And now let's compute the minors. Let's look at the first one is 1, 2, 2, 4. And we'll consider the first one, which will consist of the first 3 columns. So 1, 2, 2, 4, 5, 8, and 3, 1, 6. Surprise. It will give us 0. Let's go look at the second one. Surprise, it will give us 0. So I take columns 1, 2, and 4. As you can see, there is no point of taking the others because they'll be proportional. Basically, it will be the same thing. The determinant, since we apply some properties of the determinant here, if you look at them, the columns 2 and 3 are proportional, so the determinant will be 0. Anyway, these minors of order 3 are 0, so there is no hope for me to find any non-zero minor of order 3, so I have to stop at non-zero minors of order 2, and therefore the rank is 2, and that's it. Okay, now we're going to talk about something new. Well, it goes pretty fast when you read the notes instead of writing them. But like I said, I prefer writing rather than just reading notes. For some reason, I feel like. Anyway, so let's talk about coordinates and change of basis. And the first thing we want to talk about is the coordinate representation relative to a basis. And I'm going to denote a basis B, which will consist of these vectors, v1, v2, vn. And I say this will be an order basis for a vector space V. And let me consider a vector x in V, such that this vector x in V is a linear combination of these vectors in the basis B. And as you can see, the linear combination is written in this form. So x is c1 v1 plus c2 v2 plus cn vn. And these scalars, c1, c2, cn, are nothing else than just the coordinates of x relative to the basis B. And now we can write the coordinate matrix, or the coordinate vector, whatever you want to call it, of x relative to a basis B. And basically, this is nothing else than just the column matrix in Rn, whose components are the coordinates of x. So we can write them like this. So this is the coordinate. That's why, well, it doesn't matter what do you prefer. If you can call it coordinate matrix, coordinate vector, it doesn't really matter. And it will be this will be the coordinates of x relative to B, which are as c1, c2, cn. And now in Rn, we will use the column notation for the coordinate matrix. For a vector x, which is in Rn, the x1, x2, xn, the components xi's, these are the coordinates of x relative to the standard basis s in Rn. So we will write them in this way. you see the vector x relative to the standard basis S will be x1, the column vector x1, x2, xn. Now let's give an example. Find the coordinate matrix of a vector, and then I have this vector x is 1, 2, -1, so I'll consider this vector in R3 relative to the non-standard basis. And of course, I will consider this basis B prime, like I said, non-standard basis, B prime, which will consist of these vectors, U1, U2, U3, which these are vectors in R3. And the first one is 1, 0, 1. The second one is 0, -1, -2. And the third one is 2, 3, and -5. Okay, I want you to look at it. So how should we approach this? Well, let's look at this vector x is 1, 2, and -1. So the first thing I need to do is to write vector x as a linear combination of these vectors in this non-standard basis B prime. So let's do this. So I'm going to write them like as a linear combination. This implies that this is nothing else than just x equals C1 of U1 plus C2 U2 plus C3 U3. And again, we're doing all these computations here. And once we do this, we know who x is, we know who U1, U2, U3 are. And then at the end of the day, we'll end up with the following system. Again, we'll go back to the system of this system of linear equations. As you can see, I have it's a 3x3 system, and I can solve it. I can do whatever I want, or I can write this in the matrix form. And I will leave it to you as an exercise to show that this has indeed a unique solution, which is given by C1, C2, C3, and this will be the vector 5, -8, -2. So x can be expressed in this way as a linear combination, right? And the coordinate matrix of x relative to the basis B prime is this guy here. It will consist of the vector 5, -8, -2. Well, pretty straightforward. Now let's see how we're going to change the basis. So the change of basis. I want to, in fact, we already illustrate this in this previous example that we just talked about. So the change of basis. So like I said, the procedure that we just described in the above example is called, in fact, the change of basis. What we just did is the following. Let's rewrite this. So as you can see, I wrote this matrix P, right? And let me just go back. As you can see, I formed this matrix. Where is it? Okay, here. Right, as you can see it. So I formed this matrix 1, 0, 2, 0, -1, 3, and 1, 2, and -5, right? And we'll denote this by P. And then I multiply with the vector in the basis B prime, which is C1, C2, C3, and I know that this will be equal to 1, 2, and -1. And again, the matrix P, we'll call this matrix P the transition matrix from the basis B prime to the basis B. That's what it is. And now we want to see how to perform a change of basis from B to B prime. Well, guess what? since the matrix P will perform a change of basis for B prime to B, and if I go, and now if I want to go back to B prime, so I want to go from B to B prime, guess what? That change of basis is performed by the inverse of P. So we need to make sure that that matrix P is invertible. So as you can see, this is performed by P inverse. So this is how the matrix, how we perform the change of basis from B prime to B and also from B to B prime. So we need to find the inverse. Well, we can find it, and well, I'll leave it to you as an exercise, but I already, to show that the inverse is actually this matrix here. It's -1, 4, 2, 3, -7, -3, and 1, -2, -1. So this matrix, the inverse of P, will perform the change of basis from B to B prime. Now the question, well, we can actually generalize this discussion. Let's assume that B will consist of these vectors. If just instead of having 3 vectors, we can have n vectors. Let's assume that B will consist of these n vectors, v1, v2, vn. And B prime will consist of u1, u2, un. So we consider these 2 ordered bases of Rn. And now if I consider x to be a vector in Rn, and I know that this vector x relative to the basis B is given by c1, c2, cn, and the vector x relative to the basis B prime is d1, dn. So these basically are the coordinate matrices of x relative to the 2 bases. Then the transition matrix from B prime to B is the matrix P such that the coordinate matrix of x relative to the basis B is it's the matrix P times the coordinate matrix x relative to the basis B prime. Okay, that's pretty much what we have talked about. And now we have the following theorem. If I have a matrix P, and this is the transition matrix from a basis B prime to a basis B in Rn, then this matrix P is invertible. So this transition matrix is invertible. Because we said previously, how do I know that this is invertible? Well, it is. And moreover, the transition matrix from the basis B to B prime is given by the inverse. I want you to look at this theorem because it's important, and we will use it in applications. Okay. But before we go, we also have the following dilemma. So if I have a basis B, which will consist of vectors v1, v2, vn, and B prime will consist of vectors u1, u2, un. So I have these 2 bases for my vector space V, and I can write the first vector as a linear combination of the vectors in the second, from the second basis. As you can see here, v1 is c1, 1, u1 plus c2, 1, u2, and so on. And then the transition matrix from B to B prime is given by this matrix Q, which will consist of these, will have these entries: C11, C12, C1n, Cn1, Cn2, Cnn. So it will be an n by n matrix. Also, keep in mind that Gauss-Jordan elimination can be used to find a transition matrix, the inverse, P inverse. All right, so we have the following theorem. If I have a basis B, which will consist of v1, v2, vn, and another basis B prime of vectors u1, u2, un. So I have these 2 bases in Rn. then the transition matrix P inverse from B to B prime can be found by using the Gauss-Jordan elimination. So this goes back to the first chapter, the second lecture, a long time ago, but we have used this procedure over and over and over again. So we can perform the Gauss-Jordan elimination on the n by 2n matrix B, B prime. So as shown below here. So if I put these two bases here, B prime B, this will be the n by 2n matrix, which will consist of the identity and the inverse. And now, well, this is notation maybe, well, you have been used with this notation, but let's see an example. Let's look at this example. So we need to find the transition matrix from the base B to B prime for the two bases in R3, which are given below. So the first one, as you can see, will consist of this, is the standard basis in R3. As you can clearly see. In fact, we started our lecture to, yeah, we've talked about the standard basis in R3. And then the second basis B prime is not so standard, as you can see. Well, we need to find the transition matrix from B to B prime. Well, as you can as you can imagine, you need to involve the inverse of P here. So let's see. We will use the vectors in the two bases from to form matrices B and B prime. So like this. As you can see, this is both of them are 3 by 3 matrices. And next we form this matrix B prime B, and we will, just like the theorem says here, so we form, in this case, we'll form this matrix 3 by 6, and we'll perform Gauss-Jordan elimination to these matrices, so element transformations, to rewrite B prime B, as we can, to the identity times a matrix. So like again, this, after we do this, we'll get the following. As you can see here, I have the identity. This guy here is the identity, and this guy here will be the inverse of P, as we can identify. Right? That's pretty straightforward. So the transition matrix from B to B prime is nothing else than just this matrix right here. This 3 by 3 matrix, -1, 4, 2, 3, -7, -3, and 1, -2, -1. All right, let's see another example. And this time I'll take two bases in R2. And again, I want to find the transition matrix. Why did I write it twice? Wow. The transition matrix. Wow. Well, anyway. I don't know what I was thinking. When I wrote this, and when I thought that I was doing this video, it was very late, very, very late, just like now. So probably I did not. So the example is, I want to find the transition matrix from B to B prime for these two bases. Again, I'll do the same thing. Keep in mind that I want to use this. Just keep in mind, look at it. I want to use this theorem. I want you to look at it to see. And once I form this n by 2n matrix, so in my case will be a 2 by 4, I perform Gauss-Jordan elimination. So let's go back to our example. So let's write this matrix. So it's a 2 by 4. Which will consist of B prime. And again, using Gauss-Jordan elimination, we'll find the transition matrix. As you can see again, this is the identity, and this is my P inverse, which is this. Guys, I think I will stop here. Thank you very much. I'll see you next time.